You're ready. Bismillahirrahmanirrahim. Assalamualaikum and a very good morning. Can you hear me?
Waalaikumsalam, Doctor. Yes, Doctor.
Can, All right. So, can we start the lecture? I see not many today, Only about 80 something participants. We got a test this morning for AJ. Okay, tak apa. So, let's start. So, today's lecture is on antimicrobial chemotherapy. Okay. I'll share slide. Okay tak? Hello.
Okay, Doktor.
Okay, so soft. Raihana. Okay. So the learning outcomes of today's lecture, okay, number one, be able to define antimicrobial, antibacterial and antibiotic. Be able to describe the principles, so this is very important, the principles of antibiotic use or antibiotic selection. Number three, be able to describe the mechanism of antimicrobial action. I think this has been taught in your bacteriology, but never mind, it'll be a revision. Today, I will just go through on that very fast. Laser pointer, okay. So the aim of antimicrobial chemotherapy, is to treat acute, severe, persistent. That means it's there for a long time, and progressive infectious disease. Okay. So what are the principles of antimicrobial selection? Number one, susceptibility testing. Okay. So I'll record this. Hang on a minute. Stop the video. Okay, susceptibility testing. So the results of this test, establish the drug sensitivity of the organism, and we are able to predict the MIC. MIC refers to the minimal inhibitory concentration. Okay, usually this test, susceptibility testing, can be determined by disc diffusion Kirby-Barrett method or by broth dilution. Okay, so with broth dilution, we are able to determine the MIC values. It doesn't go to the next slide now. Just something is not right. Lagging. I don't know why it is. Okay, never mind. Yeah. Doesn't go to the next slide. Tu dah jam pula ni. Sekejap I don't know what's not right here.
Doktor.
Yes.
Cuba Doktor pergi ke bawah belah kiri.
Bawah kiri kiri okay.
Tu ada kat situ.
Oh ni tekan ni je Oh,
pakai tu pun boleh.
Oh, okay. Sebab kebiasaannya saya pakai enter. Tapi cuba yang ni okay. Tak juga.
Oh.
It's not moving. Is it because of the laser pointer or what? I disable it. Yeah. Wait. Okay. So I only can use the one at a time. Dapat yang ni I pakai cursor je lah. Yeah. So okay. So gram-positive, yeah. Gram-positive bacteria, they have a thick outer wall, yeah. It's composed of a number of layers of peptidoglycan. Okay, so the walls, yeah, of this gram-positive bacteria are made of peptidoglycan. Okay, therefore antibiotics, yeah, that interfere with the peptidoglycan synthesis can easily reach the site of action. Okay. Okay, whereas the gram-negative bacteria, yeah, they have pores. Tekan dia anu pula. This one, how to, yeah. So the gram-negative bacteria, yeah, they have pores in their outer membrane. Okay, that will allow the passage of small hydrophilic molecules. Okay, the anaerobic organism, okay, this organisms, they have gram-positive anaerobic, yeah, gram-negative anaerobic, yeah. So this organism, yeah, they cause extensive tissue necrosis, yeah, limiting the penetration of antibiotics to the site of action. So when we choose antibiotic, yeah, for treatment, so we must determine, yeah, the characteristic of the bacterial agent. Is it a gram-positive aerobe, gram-positive anaerobe? Yeah. If you use a drug that is sensitive against a gram-positive aerobe, yeah, to treat an anaerobe, it won't be effective. Yeah. Okay, some bacteria have highly predictable sensitivity patterns, yeah, because their lack of ability to acquire resistance. Okay, so some you can predict the sensitivity. Okay, so for this organism, okay, this is the antibiotic. What are the common antibiotics used? Yeah, so for example, like Clostridium species, yeah. So penicillin would be the drug of choice. Rickettsia, we use tetracycline. So for rickettsia, if you suspect, based on the culture, yeah, the results, yeah, and the sensitivity testing, if you found that it's rickettsia, and you are using like penicillin to treat rickettsia, then there will be a problem. So selection of antibiotics is very important according to the organism that has been isolated or cultured. Okay, so for example, rickettsia, the antibiotic that works against rickettsial organism is tetracycline. Okay, so the use of antibiotics, yeah, can also contribute to the bacterial resistance in animals and complicate, yeah, the treatment of diseases caused by antimicrobial resistant bacteria. Okay. So usually the use of antibiotics, yeah, which can lead to this bacterial resistance, yeah, is when you use antibiotics, misuse of antibiotics. Inappropriate use of antibiotics can lead to bacterial resistance. Okay, like underdosing the antibiotic. Yeah, I mean giving less than required to treat an infection. Okay, that could lead to the persistence of the antimicrobial resistant bacteria. So the bacteria doesn't die. Yeah, so they live and then they become resistant, and they pass on the resistance to other bacteria around them. Okay, so when you give antibiotics for the second time, it won't be effective. Okay, because there's more resistance towards the antibiotic that was effective at the first time. Okay. Okay, so human health, yeah, due to this antibiotic resistance, Okay. So on the human health risk, so bacteria can transfer resistant to each other. Bacterial resistance, to animal drugs, can become resistant to similar human drugs. So we can acquire from the animals, drugs that have been used in animals, and animals has got the resistant bacteria, and this resistant bacteria can be passed to humans. Okay, that is the human health. We are at risk lah. Okay, so we must be careful when we use antibiotics in animals. Okay, because the organism in animals, the bacteria can become resistant and pass on the resistant bacteria to humans, and then the drugs that are available, wouldn't be effective to treat human infection, right? So bacteria resistant to antibiotics can spread to people in several ways, including eating or handling contaminated meat, meat that has been contaminated has got the resistant bacteria. Contact with farm workers, who handle contaminated animals or meat. Okay, so the farm, has got the resistant bacteria, and food workers. So these people who work in the farm, they must take care of their hygiene. So if they are cleaning their hands all the time, washing and preventing infection and so on. So this problem, wouldn't be there. But if they handle these contaminated animals, and meat, and they don't wash their hands, then there is a possibility of them getting the organism. Okay, so sometimes this contaminated meat, this organism can be destroyed, after cooking, but must be proper cooking lah. Okay, like it means if you cook at there are different types of cooking for meat, well done, then that means everything will get killed. Usually if you cook curry, okay, you are safe, no problem. Because you boil the chicken for some time, you cook it at a high temperature. But for steak, especially for steak, when you have like a medium rare, medium rare, I think they call it medium rare, something like not well cooked lah. I can't remember the term. Is it rare? They call it RARE, medium rare. Have you heard of that? Anyone?
Yes.
Yeah, they call it rare, lepas tu, and then medium rare, and then medium, and then well done. So here there is a possibility when the meat is not cooked properly, the resistant bacteria can survive. And when we eat the meat, we consume the resistant bacteria. Okay, so contact with soil, and water, that has been polluted by animal waste, usually like E. coli and so on, will be passed down in the feces. Okay, so if the soil is contaminated, the water contaminated by the animal waste could also contribute to the the spread of the resistant bacteria to human. Then breathing air vented from facilities using antibiotics non-therapeutically. So this is actually using at low dose, like in growth, as growth promoters, and for a long time, could lead to the spread of this resistant, and then the bacteria become resistant, when it's being used at a very low dose. So that's why now worldwide concern that antibiotic growth promoters, should not be used. And in Malaysia we are still using, but slowly we are phasing off lah. Okay, so we have started with colistin. We have the Department of Veterinary Services, they have banned the use of colistin. Colistin is an antibiotic, which is now it has become the last resort of antibiotic lah, for to use in human, yeah, for severe pneumonia in human. So they want to reserve this antibiotic for human use. So therefore they have requested, yeah, the Ministry of Health, yeah, together they have requested to the Department of Medical Services to ban the use of colistin as AGP, okay, antimicrobial growth promoter. Okay, so slowly we are trying to cut down the use of antibiotics as growth promoters, yeah, in Malaysia. In EU countries, yes, there's a total ban of antibiotics as growth promoters, right? And yeah, the bottom line, yeah, and so anybody can be at risk. Okay, the drug concentration, yeah, at the site of infection, yeah, depends on the physiochemical properties of the drug, such as lipophilicity, ionization, plasma or plasma protein binding, yeah, or tissue binding, yeah, of the drug. Okay, and also based on the physiochemical characteristic at the site of infection, yeah. For example, yeah, inactivation by necrotic tissues, yeah, biofilm. Okay, so biofilm is usually when there is only a layer or a thick layer or community of bacteria, yeah, um, adhering on the surface. Okay, it's not only a single bacterium, it's a community of bacteria. That means there's a layer of bacteria on the surface, that is a biofilm. Then granuloma, okay, granuloma is usually, it's a process where the inflammatory cells or immune cells, yeah, they will surround the infectious agent. Okay, so sometimes that can limit the penetration of the antibiotics, yeah, to the organism. Okay, and then blood-brain barrier, yeah, this one I've discussed before. And the third one is potential toxicity. Okay, so this one related, specific drug related, yeah, such as aminoglycoside. Yeah, aminoglycoside can cause renal toxicity. Yeah, so not only renal toxicity, it can also lead to ototoxicity. Yeah, toxicity of the ear. So this one toxicity results from the progressive damage to the cochlear sensory cells and the vestibular cells in the ear. Okay, due to the damage of the cochlear sensory cells and vestibular cells, yeah. And then the renal toxicity, yeah, or also referred as nephrotoxicity, yeah. This is caused by the damage, yeah, to the proximal tubular cells, yeah, and resulting in proteinuria. Okay, and then this will lead to impairment of the absorption and also reduce GFR glomerular filtration rate. Okay, that's aminoglycoside. And fluoroquinolone, yeah, usually fluoroquinolone, yeah, it's not given to young growing dogs, okay, because it can cause damage to the cartilage, right? And other factors are the host factors, yeah, the immune status of the animal, yeah, the hepatic and the renal function, and also the age, yeah, of the animal. Okay. So all these three factors, yeah, I have discussed in detail when I was talking about factors that affect the metabolism of the drug. Okay. Okay, this one, yeah, it's on the governmental rule regulation line food animal, yeah. So we need to adhere to the Food Act, yeah, 1983, yeah, and food regulations, 1985, yeah. So it's in that act, yeah, it stated the maximum permitted proportion of drug residues. So MRLs are indicated, yeah, in the Food Act for meat and milk. Okay, you can refer to the act, yeah. And MRLs, they differ, yeah, they differ for each drug, yeah, or antibiotic, yeah, animal species, and also in tissues. Okay, so it's very detailed. Detailed information can be obtained from the Food Act and the Food Regulations 1985. And drugs such as beta agonists. Yeah, have you heard of beta agonists? Anyone?
Yes,
Hello.
doctor.
Have you heard of beta agonists?
Yes.
Yes, okay. So drugs, yeah, like beta agonists, yeah, but excluding ractopamine lah. So all the beta agonists drugs are banned, yeah, to be used in animals, in livestock animals, yeah, excluding ractopamine. So only ractopamine, yeah, is allowed to use as a growth promoter, yeah, in livestock animals. So mainly, this ractopamine is used in the in pigs, yeah, mainly in pigs, I think, yeah. We don't use much in the cattle, okay. So only ractopamine is allowed, yeah. Others are all banned, yeah. And nitrofurans, okay, they are also banned for systemic use in poultry, yeah, and swine, yeah, because it can lead to some kind of a problem which which causes cancer, yeah. It's carcinogenic, yeah. Okay, and then the chloramphenicol, yeah, this is another antibiotic, yeah, that has been banned, yeah, not only in Malaysia but also in European Union and many countries, yeah. So it's being banned for the use in food producing animals, yeah, because due to the effect, yeah, the suspected effect of carcinogenicity, yeah, and also it has got links, yeah, with the development of aplastic anemia. Okay? So aplastic anemia, yeah, in humans, so therefore they have used the ban in food producing animals. Okay, so aplastic anemia is a serious blood disorder. This is due to apa ni, the bone marrow, yeah, they are unable to generate new blood cells. Okay, so that is with this chloramphenicol. Okay, so all these drugs, actually they are banned worldwide. In many European countries, not all, I would say, yeah? In many of the European countries, yeah, including in China, and then Malaysia also have taken the step, yeah, to ban this drugs, the use of these drugs in food producing animals. Okay, so the next point is the drug interactions, yeah. So synergistic effect, yeah. For example, like beta lactam. Okay, you want to use drugs, two drugs, yeah, at the same time. But some drugs, yeah, like this beta lactam and aminoglycoside, they come in a combination preparation. Yeah, I think I've shown the slide earlier. Let me show you. This one. Okay, so penicillin is a beta-lactam drug. Yeah, streptomycin. Yeah, is a aminoglycoside. So the combination of penicillin and streptomycin will produce the synergistic effect. Okay, what is synergistic effect? It's the plus effect. Okay, so this is for injection. Yeah, it's in the suspension form. Okay, that's beta-lactam and aminoglycoside. And drugs, you must be very careful too. Yeah, drugs also have got the antagonistic effect. Okay, for example, yeah, a bacteriostatic drug, yeah, drugs may decrease the efficacy of a bactericidal drugs. So if you give a bacteriostatic and a bactericidal, it's not ideal. So here is actually the beta-lactam. Yeah, I like to use the laser pointer. Nampak cantik sikit lah dengan background biru. So here, the beta-lactam penicillin is a bactericidal drug. Okay, aminoglycoside is also a bactericidal drug, right? So they produce synergistic effect. But here, yeah, tetracycline is a bacteriostatic. It produces bacteriostatic. Yeah, you understand about bacteriostatic and cidal. Static inhibits the replication of the bacteria. Penicillin, which is a bactericidal drug, yeah, kills the bacteria. Right. So giving the combination, like tetracycline, it is not in a combination at the moment, but if you prescribe, to dogs or cats, tetracycline and penicillin, to be given at one treatment protocol, so that it be useless, the treatment won't work, okay, because tetracycline has got the effect that it inhibits the replication of the organism, all right, the bacteria, whereas this one will kill. But penicillin, if you look at the mechanism why it has got the antagonistic effect, because of the mechanism of action. Okay, so penicillin only works on actively dividing cells. Okay, if the tetracycline inhibits, therefore penicillin would not work on the bacteria. So therefore, tetracycline will reduce the efficacy of the bactericidal drug, which is penicillin. So in this case, it actually penicillin is more important as compared to tetracycline. Right? But the bactericidal activity is of importance as compared to the bacterial static. Right? So what?
Doctor, can I ask?
Yes, doctor.
Yeah.
When do we use the bacteriostatic drugs?
Bacteriostatic drugs, they are given, according to the infectious agent. Okay. For example, tetracycline is a broad spectrum antibiotic. That's effective against chlamydia, rickettsia, which penicillin cannot work on. So you refer to the spectrum of the activity. So when you give a bacteriostatic drug, it's actually you're also depending, on the mechanism, the body mechanism to eliminate the infectious agent. Here, there's killing of the bacteria, but here it inhibits the replication of the bacteria, and followed by the immune system to get rid of the organism. Okay, all your immunological reaction will also be working towards to eliminate the bacteria. Is that okay?
Yes, doctor. Thank you.
Right. Okay, so this was the example just now, yeah. And so antimicrobial drugs, okay, these are the drugs that some will kill, some, so the one that kills, yeah, is referred as bactericidal, okay, because it can be a virus, it can be a protozoa, it can be a bacteria or virus or fungus or so on. So anything that kill will be a acidal, inhibit, yeah, static, okay, growth of organism or microbes such as bacteria, protozoa, virus, and fungi. So it can be from the natural source, yeah, or from synthetic, that means being produced in the lab, yeah, using the formulation, yeah, of the chemical. And they are toxic to microbes at a low concentration, right? So usually if you give it in a high concentration, definitely the patient will come down with the disease. So it's usually they are given at a very low concentration. The types of antimicrobials, yeah, I've mentioned earlier, cytostatic, yeah, it kills the microorganism, and the other one, static, inhibits the replication of the organism. So antibacterial is a broad term, yeah. So this is referring to an antibacterial agent, yeah. Any drug could be from synthetic or natural, yeah, with either a static or a cidal effect on bacteria. Antibiotic, yeah, it's a chemical, yeah, that's produced by microbe, okay. So it's actually a microbe to combat another microbe, huh? Okay, so toxic to microbes, yeah, at very low concentration. Okay, just to show you, yeah, the sites of antimicrobial action. Okay, you can recall your microbiology lectures, yeah. So this antimicrobial agents, they act on the, where do they act on? Anyone? Where are the 5 sites that an antimicrobial agent act on? On a, let's say on a bacteria. Hello, tak ingat dah.
The cell wall.
Cell wall, yes. Yeah, so the cell wall, yeah. And then the plasma membrane, yeah. Some act on the plasma membrane. Yes, some act on the DNA of the bacteria. Okay. Drugs that enter, yeah, and act on the DNA are very potent drugs, yeah. Okay, and then the others would act on the protein, yeah, the ribosomes. All right, and the last one would be the the drugs, yeah, that have that can alter the metabolism, yeah, the metabolism process of the bacteria. So these are the sites where this antimicrobial agent can act on. Cell wall, plasma membrane, DNA, ribosome, and on the metabolic activity of the bacteria. Okay, the categories of antibiotics, yeah. Okay, I mentioned this is they kill the susceptible bacteria, okay, static, they inhibit, yeah, the growth, yeah, or the replication of the bacteria. So in general, the use of bactericidal antibiotics is preferred, yeah. Okay, so here we have, excuse me, bactericidal and bacteriostatic agents. So the killing mode of the bactericidal agents, yeah, are dependent on the 2 types of killing, yeah. One is referred as the time-dependent killing, yeah. Another one is the concentration-dependent killing. Okay. And as for bacteriostatic, yeah, they're all time-dependent inhibition. Okay, so mode of action, yeah. So as I mentioned earlier, it's the inhibition of cell wall, inhibition of the cytoplasmic membrane synthesis, inhibition of DNA replication, inhibition of protein synthesis. All right, so this is with the antibactericidal agents. Okay, and time dependent. Okay, we have inhibition of protein synthesis, and I'm losing my voice. I think it's asking me to sing a song. Dah serak dah suara. Okay. Right. Let me just take a sip of water. Okay. Right. So as for time, yeah, bacteriostatic agents, it's inhibition of protein synthesis, yeah, the mechanism, and also modification of the energy metabolism. Okay, it interferes with the metabolism of the bacteria. Okay, right. So the classes, yeah, that inhibit the cell wall synthesis is beta lactams, right? And the bacterial life cycle that are affected, yeah, is the proliferating bacteria, right? So as we know, if you look at the cell cycle, okay, we have like growth phase 1, yeah, and then the organism can go into the resting phase. This is GO, and followed by synthesis. Okay, this is a very important step in the cell cycle. So this is where the DNA is being produced, yeah, and followed by second growth phase. Okay, G1 and G2 refers to growth phase, and followed by cell division or mitosis. Okay, so this is the cell cycle, right? And then so the cycle that's affected, yeah, is the proliferating bacteria, and with the cell membrane, yeah, drugs that inhibit the through the inhibition of the membrane, yeah, leading to the death of the microorganism are the polymyxins. Okay, so polymyxins we have B and E. Okay, so E is the drug, yeah, just I mentioned just now, colistin, yeah. So this drug has been banned. The use of colistin in livestock animals has been banned in Malaysia and elsewhere lah, okay, even in other countries and so on by WHO, because this colistin is the last resort of antibiotics. Yeah, it's an old drug, you know, but we are going back in a cycle because we don't have many antibiotics available now. Yeah, in order to produce one antibiotic, it takes like 10, yeah, 15 to 10 to 15 years of research coming out with antibiotics, and within 6 months, the antibiotic develops resistance. It's so sad, isn't it? So that's the problem. So we must use antibiotics very, very carefully. All right. So we are going back to the old antibiotics. This is the old that has been used quite extensively in the 60s. Yeah. And then because of some side effects, we have stopped that. But we are going back lah. We are going back to this antibiotic. And so it's a very important antibiotic in human medicine at the moment. So it's going to be the last resort of antibiotic for severe respiratory disease, yeah, in human, yeah, related to pneumonia. So therefore, it has been banned in the livestock animals. And with concentration dependent, we have these two drugs, yeah, fluoroquinolone. Okay, so this drug, yeah, shouldn't be the first line of antibiotics, yeah, to be given to animals, yeah. So because this is a very new drug and very potent, we should always start, with the antibiotics that are not so potent. Because if we use everything and then we cannot fall back, we don't have any other antibiotic to use on patients. So usually, penicillin group, is the first line of antibiotics. Penicillin, tetracyclines, these are the first line of antibiotics, and these are used when there is apa ni, when the animal is already resistant, has developed resistance to the first line antibiotics, such as the penicillin group. All right. So fluoroquinolone, it acts on the DNA aminoglycoside, inhibits the protein synthesis. But with aminoglycoside, common side effects, nephrotoxicity, I mentioned just now. So we must be careful when we use aminoglycoside. And then inhibition of protein synthesis. This the tetracyclines, phenicols, the chloramphenicol that I mentioned just now, which is banned drug too, in livestock animal, macrolides, and lastly would be the sulfonamides. These are sulfur drug. Okay, so the bacteriostatic agents, mainly they act on the proliferating bacterial life cycle, whereas the one act on DNA and protein synthesis, which has the killing ability, will act on the stationary and proliferating bacteria, and the one that act on the plasma membrane, will act on the stationary cycle, of the bacteria. Okay, so far so good, So far so good.
Yes, doctor.
Yes.
Yes, okay. So we
Yes,
will look.
doctor.
Okay, right, good. So we will end soon. We got 10 minutes. I think we got lecture after this, right?
Yes,
We got
doctor.
yes. Only on Fridays you don't have lecture. Okay, never mind. I will finish this quite quick. So just to show on bacteria killing, bacteria killing of drugs, we have two just now, the concentration dependent and time dependent. This is like further to explain so that you understand better. So this graph actually is taken from a research work done by my colleague. So what he has done, he has looked at the concentration dependent bacterial agents and also the time dependent. So here, as you can see, the y-axis is the log CFU coliform forming unit per ml. So this is the bacteria unit. Here versus time. And as you can see, the blue, the yellow, the yellow line here, this is the there's a control, it's just the bacteria, okay, bacteria, it shows, bacteria without treatment, right? So it shows a rise, in the coliform forming unit CFU, okay, is increasing, okay. Whereas we just look at, we don't have to look at the quarter MIC, we just look at the 1 MIC and 4 and 16. We just concentrate on few here, 1, 4, and 16 to get a clear picture. So here the purple line, okay. So it was treated with the MIC, the minimum inhibitory value, concentration, okay. So it inhibits the bacteria. Okay, you see, this is rising, this has dropped, okay, and then followed by 4, Okay, this is quarter MIC, yeah, according to him, yeah, according to the legend here is quarter MIC. So one MIC, yeah, it has the CFU as decline. Yeah, if you look at the control and treated with the minimum inhibitory concentration, yeah, of the drug, yeah, it has decline, yeah, and when followed by 4 MIC. So if the MIC here given is let's say 2 microgram per ml, so 4 MIC 2 times 4 will be 8 lah. Yeah, the concentration of the drug is 8 microgram per ml, and then if it's like 16, just times 16 times of the MIC. Okay, so when the concentration, yeah, of the MIC is being increased, yeah, from 1, 4, 16, and he did 64 times of the MIC value. So you can see, the colonies of the bacteria is reduced tremendously as compared to the control, isn't it? So this shows the concentration dependent killing. You increase the concentration, yeah, there is a decrease in the bacteria. Okay, so here this is 1 MIC, and if you treat it like 4 times of the MIC, there is more pronounced decrease of the bacteria, and it's dependent on the concentration. You increase the concentration, it inhibits the bacteria according to the concentration. High concentration, high killing of the bacteria. Okay, so that is concentration dependent killing. All right, whereas this one, yeah, time dependent. Okay, again, this is the control. Yeah, no drugs was given. So this is the bacteria, and this quarter MIC. Okay, we look at 1. Okay, at 1 MIC concentration, the minimum inhibitory concentration, yeah, it shows decrease. Decrease in the coliform forming units, yeah, the bacteria. And when we increase the concentration, yeah, 4 times MIC, and 16 times and more, we can do more here, okay, 100 times of the MIC and so on. But we can see the pattern, yeah, immediately, yeah, after the 4 MIC, there is no difference, yeah, between the other, what do you call, the other lines. Okay, there's only different, yeah, within 1 MIC, yes, yeah, because this is completely no drug, yeah. So here, given the concentration is 1 MIC, when we increase the concentration, no effect on the killing of the organism. Right? So therefore, it is independent of the concentration given. So if you give how high the concentration, it wouldn't work. Only thing it will lead to toxicity lah, because the drug usually, when it's being formulated, it is taken into consideration, yeah, the therapeutic effect and the side effects must be a balance. But if you increase, you will cause more toxic effect to the animals. Okay, so therefore, yeah, it's only those who are not dependent on concentration, those bacterial agents that are not dependent on concentration, they are time dependent. So they are given at certain intervals to kill the bacteria. Okay, boleh tak? Can you all understand this?
Yes, doctor.
Yes.
Okay, good. So only these 2 concepts very important for the bacteria killing. Okay, this is just a repetition. Yeah, I have mentioned earlier. Yeah, on the drugs that act on the, why is this thing comes down? Okay, cell wall synthesis. Yeah, the penicillin and cephalosporin, on cell membrane polymyxins, DNA fluoroquinolones. Yeah, And then on the sulfonamide, okay, sulfonamide is actually affect the metabolic activity of the bacteria, okay. So sulfonamide is a PABA. I'll explain this in my next slide. Now is PABA. It's a PABA antagonist, all right. And then we have the trimethoprim. Okay, sulfonamide is always given, sometimes it's given by itself, but also in combination with trimethoprim to produce the synergistic effect. Okay, so trimethoprim is a dihydrofolate reductase inhibitor. It also alters the metabolic activity of the bacteria. Okay, so I'll explain this too, the sulfonamide and trimethoprim, perhaps next week lah. Okay, because it's already time. It's going to be 10. Okay, so tetracycline, okay, okay, they are protein inhibitors, they are 30S protein inhibitors, and then this is 50S inhibitors, protein inhibitors, chloramphenicol and fluorophenicols. Okay, I think this is my last slide. Oh yeah, I got one more. Sekejap, I tengok lagi. I think I will explain this tomorrow lah. Okay. Is there any questions so far?
None from me, doctor.
Say again, tak clear.
None from me, doctor.
Okay, who's speaking? Oh, Raja, Raja.
Raja, yeah.
Good, Raja. So if anybody like have any questions, you also can consult Raja, because Raja is the only one who understood my lecture. Are all okay or not? All so quiet today.
Okay, doctor.
Okay, doctor.
All okay, Okay. So I see you tomorrow lah. Okay, tomorrow at 10 o'clock, right? We got a lecture at 10. It's almost 10. Yeah. So okay, then I will stop the recording and you can leave the meeting. Yeah.